Next slide. Oh, sorry, then we can heat it up, evaporate off the water and the carbon dioxide, keep going. And we can see the pure spectrum of carbonic acid. That occurs on Mars. The ice caps on Mars are basically water and CO2. They are irradiated. In the summer, the water and the carbon dioxide evaporates, and you can see the carbonic acid. India goes to Mars. India has sent probes to Mars. India is looking for things on Mars. So some of this work can and will be done in the future, and the PRN is designing the next generation of experiments and probes to do it. Next slide. So, the conclusions so far. We can make small molecules. We know the theory, these dust grains and irradiating the ice, we can make the small molecules. Can we make the larger biological molecules? Next slide. Yes. This year we've shown that. This is Bose, this is a sugar in space. This is the man who did it, a good friend of mine, Uwe Meyer-Heinrich. This is the sort of apparatus. Look at that, go and see the one in Barla's lab, it will look very similar. There's the newspaper article, complex sugars cooked up from comet ice, okay? So, we can make these molecules. Next. So we can create an amino acid, we can create a sugar in space, and synthesis works. Next slide. So we can simulate. We can show it makes. What it means is the first conclusion. This chemistry will be the same anywhere in the universe. The rules of chemistry and physics apply anywhere, so chemistry will be done anywhere, so we can make these molecules in any solar system, about the stars, these molecules, anywhere we can make them. There's nothing special about the Earth, there's nothing special about the solar system as we live in it. But what does it tell us about the life on Earth? Next slide. How do these molecules assemble to make DNA? Question for you. Can anybody tell me how these molecules might assemble to make DNA? I've made my acids. I've made my sugars. I've made my amino acids. I've made the nuclear bases. How do they assemble to make the DNA, which is the molecule that we need to reproduce and do everything? Anybody tell me?
Aggregation and polymerization.
Pardon?
Aggregation and polymerization.
Polymerization, okay. Where?
At the reactive functional groups.
Right. But you haven't told me the exact mechanism where it was made on Earth. How did it happen? Next slide. We don't know. If you told me, I would take that idea, run back to the UK, do the experiments and get the Nobel Prize. We don't know. We haven't done those experiments. We may have got ideas, as you'll see in a minute. Now, I thought we should have a little bit of philosophy. Okay? Because some of you, this is Donald Rumsfeld. He was the American Minister of Defense during the period of the Iraq Wars. And he said the following. And I want you to think about this over the rest of the weekend. Okay? There are the known knowns. These are the things that we know. Okay? You'll accept that? There are things we know. Yes? You're sure? Absolutely sure? Not sure about you. There are things you know. Second thing is, there are the known unknowns. That is the things we know we don't know. You don't know, some of you in the room, probably, most of you, don't know who you're going to marry. You don't know how many children you're going to have. You don't know what job you're going to do. Right? You know it's going to happen, probably, but you don't know what. It's a known unknown, yes? Now, so that's good. The problem in science and the problem in astrobiology is, and this is the deep philosophy, okay? There are also unknown unknowns. That is, there are things we don't know that we don't know. Now I want you to think about that deep philosophy, right? As soon as an unknown unknown becomes a known unknown, you can test for it so it becomes a known known. Alright? So this is your deep philosophy, okay? But it's very important in astrobiology, or in the origins of life. We know that DNA was assembled, but we don't know how. And the missing picture is, there's something which we don't know, which if we became something we knew we didn't know, we could then work out how something we know, DNA, was made. That's very difficult to say when you're tired, okay? So I want you to think on that, okay? And apply it to your lives, okay? So just think about this for your life and think about your unknown unknowns, okay? You can write that on your exam paper later. This is an unknown unknown. Next slide. But people have started to think about this, and it comes down to these suggestions. Remember apart in the early oceans? We now have these smokers at the bottom of the oceans, okay? This is where we think that maybe life might have begun. India is, there are ships that run out of Pondicherry, or whatever it is called now, where they go into the Indian Ocean. In the Indian Ocean there are these smokers. People go there, they take soundings of them. They're in the Pacific, they're in the Atlantic Ridge, they're where continental shelves, continents meet each other. So they're trying to see what sort of chemistry and what sort of things go down there, and are there amino acids, are there nuclear bases there, is there sign of DNA, is this a place? Next slide. Another suggestion is a little bit, if those of you any geologists in the room, do I have any geologists in the room? Ooh, no geologists. If you're a geologist, you go out with your hammer and you take samples as clays. Clays are a very good material because clays kind of, that's what we call a template. Clay's molecules sort of line up on clay, and water flows through it, and there are places where the molecules might have been sort of lined up with each other to join together and react. Next slide. Other people said, well, what about these volcanic vents? What about these geysers? This is a place where these chemicals might have reacted together. We can go to Iceland, we can go to places to look at that. Next slide. One possible clue to how the molecules assemble is something peculiar about biology. So the biologists in the room should know this, but what is chirality? Can anybody tell me what chirality is?
Osmotic carbon.
What?
Osmotic carbon.
Yeah. Next slide. So it happens that life has decided to form one type of orientation. You can make molecules, go back a slide, back a slide. You can make, that is the two, a molecule could be like that, or it could be like that. They're not the same, they're like my two hands, right? They do not superimpose on each other like that, they're mirror images. Life has chosen one mirror image over the other. Next slide. So all amino acids, what we call left-handed, and all nuclear sugars are right-handed. Some of you will know the story of thalidomide, which was a drug that was brought in, given to pregnant women. It was meant to reduce the effects of morning sickness and so on. One enantiomer, one type of that, was good. The other one caused the birth defect. The drug had a mixture of the two. Life has emerged with one. If we could work out why and how the molecules did this, it would tell us a lot about the mechanism by which the molecules are formed. We don't know the full details, but again, that picture I showed a little while ago on ribose, they actually are seeing the first signs of chirality. So we're getting some early clues to that. Life elsewhere in the universe might have right-handed acids, amino acids, and the sugars might be left-handed. If you watch Star Trek, or that means alien life, if you try to get them together and produce offspring between the two, this wouldn't work. Okay? If you had that as one consequence. Next slide. So we are now back to, so let's go back to the opening question now. That's where we are in our discovery of how we develop the molecules of life. We've got so far, and now we're trying to work forward. We want to get some unknown unknowns to known knowns, etc. Let me go to the second question then, which is the other side of the equation, if you like. We found life. Let's go and see if we can find life somewhere else. If we can find life somewhere else, is it the same as us? Is it different? So let's go and look for life on another planet. I am not looking for aliens. Now, some people in America think that there are aliens. Some people think there are aliens amongst us. Any aliens in the room? I'm not sure. Those people who didn't vote yes and didn't vote no and weren't sure they're here. Yes. Do I have an alien in the back? Yes. Wow. Go and talk to him afterwards. Okay. I'm honoured. Aliens are supposed to be much more intelligent than us, so maybe if you tell me afterwards the answers to my questions, I'll get the Nobel Prize. Right. So I'm not looking for aliens normally. What I'm hoping to look for is the bacteria and possibly photosynthetic life like plants. Because if you think of the history of the Earth, we, the mammals, at the end are a very small part of the 3.8 billion years. Very small part. So for most of the Earth, if you were looking for life on the Earth, the only thing you could see is the next picture, these things, which are algae, cyanobacteria, things like that. That's what I'm looking for. These don't talk to me. Indeed, if you look at the Earth and you think about when we talk out there, until 100 years ago, we sent nothing out into space, no communications. Okay? Then radio came along. So if an alien civilization was looking at Earth up until 100 years ago, it wouldn't see any evidence of advanced civilization. It might be looking for bacteria and so on. It is a frightening thought that the first thing an alien civilization is likely to see might be the latest Bollywood movie or cricket. Now personally, I think if they were to see cricket, they would know that there was an advanced civilization here. Okay? But if they saw the cricket test matches from a few weeks ago, they might draw some conclusions. They might draw the conclusion that India is a much more advanced civilizing society because they're beating these low, very poor civilization called England. That may of course be true. Next slide. So where have we gone to look for life? We've gone to Mars. Early Mars was very similar to early Earth. It's a smaller planet, so it lost its atmosphere, it didn't have the plate tectonics. But in the first few billion years, it may have been very similar to Earth. We know that life on Earth came very quickly. 3.8 billion years the Earth was created. There's evidence for life certainly 3 billion years ago. Some people would say even 3.4 billion years ago. So at the same time, Mars might have had the same thing. We know there was potentially of water on Mars. We know there's ice on Mars. We think this is what Mars might have looked like in the old days. Next slide. We know there's methane. Methane has always been felt to be a biological signature. We know that's coming up from Mars now. And we've got some fossil evidence. Next slide. We have meteorites coming from Mars. 34 have been detected so far. And if you cut them open, the famous one is the Adam Hills meteorite. 1996, they saw these structures in the meteorite and said, oh, that's a worm. Fossilized worm. Next slide. Unfortunately, we now know it's not. But this got everybody very excited, and that's why we've gone back to Mars. India was trying to look for methane on Mars in its recent space mission, and may well do a few in the future. We want to know where that methane comes from. There are 2 American rovers at the moment. The next European rover, the first European rover, is actually going to go drill down into the Martian surface and see if there's any water down there and maybe signatures of life. Next slide. But what about other planets around other stars? This may be where we have to look. Let's not think about our solar system, let's think of another one. We know that there are planets around other stars now. 20, 30 years ago, if I'd taken a vote in the room, half the astronomers would have said there were planets, half the astronomers would have said they are not. There would have been nobody sitting here like you refusing to answer. But they would all have strong opinions. We know there are planets there because we see them go in front of the star, making a little eclipse, like that. Anybody seen an eclipse? They've been in India. Anybody not seen the eclipses in India at some time? Solar eclipses? Yes? Yes. Good. If you get a chance to see one, go and see it. Even if it's not a full eclipse, it's a wonderful experience. If you get a chance to see a total solar eclipse, it will be one of the most magical things in your life. Go and see it. So we know that. Next slide. Next slide. We know that there are at least 1,500 planets being detected. We're detecting many more every month. So we've found these planets. Next slide. We are in Europe. Oh, right. In Europe, we have a space program to go and look for these planets. And the space program is called Plato and Cheops, which is going to be 2 space missions we're going to launch, which will be capable of not only finding these planets by looking for the eclipse that they do, but also we might be able to look at the atmosphere of the planet. Exploring Mars. These are the 2 missions that are going to go up to look for planets found on the stars. This is JUICE that's going to go and look for life on the moons of Jupiter. This is Bepi Carno that's going to Mercury. Next slide, only press the button. Right. Oh! Alien, stop it! Stop it, alien. Right. So, what we want to do is to think about what we would look for on one of those planets that would tell us there's life on it when it can't talk to us. We know that water, methane and CO2 are needed for life, but the problem is we can get that on planets which don't have life on them. We know that from planets in the solar system. Many people believe that ozone is a very good biomarker. Ozone, O3, is only formed in an atmosphere which is very rich in oxygen. And the only way we know for an atmosphere to be very, very rich in oxygen in the Earth is by photosynthesis. So if you see lots of ozone in a planetary atmosphere, it was felt, therefore, there should be photosynthesis, and that was a sign of life. Dare I say, next slide. So we went to look for ozone on other planets. We found some on Mars. Next slide. But there shouldn't be, because the ozone layer that you need to build up on Mars has to be quite big, and it's never going to have got big enough to protect the surface from, that's what ozone does, it filters out the ultraviolet light to stop the ultraviolet light getting through to the surface and killing the plants by damaging your DNA. So, we saw it on Mars, we don't think there was ever enough to shield the surface. That's why we believe that life on Mars had to be subterranean. Next slide. We've recently found ozone on these moons, Ganymede of Jupiter, Dione and Rio of Saturn. Indeed, Bala and the PRL group have actually, by spectroscopy, identified some ozone on other bodies, including possibly the moon. Yeah? So, the problem is, we know that there are no trees on the moon. We've been there aren't any. We know there's no photochemistry. So this has been a problem. We thought ozone would tell us there's life. We now know that ozone can be made chemically in the irradiation of ices, so it's not unique. Next picture. So, next picture. So we've got to look for something else. And if you're looking from the satellite and Earth, particularly the ones maybe at Saturn looking back, and you get a picture of Earth from space, it will look something like this. And all these green bits